Okay, so without further ado, let me start.
Could you try to speak a bit more into the mic?
Is it better?
Yeah.
Okay, without further ado, let me jump straight in. Sorry for the technical problems. So hello everyone, my name is Dmitrii. I'm a software engineer at a company called EMQ. Today I'm going to talk about one of our projects called Mria, a purpose-built extension to the Mnesia database that adds eventual consistency to the cluster. So I need to give a disclaimer that if you attended my CodeBeam talk in Stockholm this year, then today's presentation may sound pretty familiar, so please feel free to take a nap until about the last third. So I'm going to skip a bunch of things because of time issue. I guess everyone knows what Mnesia is. I will just briefly talk about our product and how we use Mnesia. So we develop MQX, a distributed MQTT message broker. So what is MQTT? This is a little bit of context that will be relevant for the rest of the talk. So MQTT is a PubSub messaging protocol, very similar to Kafka or RabbitMQ, where the clients can subscribe to the topics and publish messages to a topic. But MQTT protocol is different because, first of all, topics are structured as a tree, similar to a file system with directories. And second, clients can subscribe not just to a single topic, but to a set of related topics through use of wildcard topic filters. And finally, topics are highly dynamic. So unlike Kafka, the topics can be created implicitly when a client subscribes or publishes a message to a topic. So another feature of this protocol is used in Internet of Things. So the MQTT brokers, such as EMQX, need to handle high volume of messages and large number of client devices. We're talking hundreds of thousands or even millions of clients. So the biggest challenge when it comes to making the MQTT broker scalable is maintaining the topic metadata. And MQX currently uses Mnesia for this task through the help of the following three Mnesia tables. Route table, RAM copies bag table containing mappings from topic filters to names of MQX nodes where the subscribers are connected to. Topic tree table, RAM copies ordered set that contains nested topic prefixes for wildcard subscriptions, and subscriber table, which is a plain adds bag table which contains mapping from topics to PIDs of local processes handling the subscriber session. Routing table and topic tree tables are accessed pretty much every time the broker receives a new message. So it is very important for us that the query time is very minuscule. And with Mnesia RAM copies, we could read the routes directly. So there were some nice pictures of how MQX routes messages. I will have to be very quick. So when the client connects, we create a record in the routing table. Mnesia replicates this record. When another client connects and publishes a message to this table, then we look up routes which match the topic in the table. and then dispatch the message to the destination. So Mnesia offers very fast, very low latency read-only queries. But things start to break down when we create very large clusters. The write latency starts to plummet. And we need high throughput for the writing records to the database as well, because imagine there was a sudden node restart or large network disturbance. So millions of clients all start to reconnect at the same time and subscribe to the topics. And we need to be able to handle it in near real time. So for years of experience, we found that Mnesia's write throughput drops dramatically as the cluster size increases. So in the next slide, I will very quickly walk through the Mnesia replication protocol and explain why it happens. Also, I need to add that a lot of our customers want to be able to scale the cluster up and down, and with Mnesia it is rather problematic because of how the schema works and how the replication works. So I will be very quick when describing transaction replication protocol in Mnesia. So it's leaderless peer-to-peer replication. All nodes can initiate transactions. Atomicity of transactions is ensured through a two-phase commit protocol. And transactions, most of the flow of the transactions is performed by the same process that calls Mnesia transaction functions, which is a decision that has pros and cons. But on the remote nodes, all operations are handled by a single process called Mnesia TM. So the process that local transactions are highly parallel, but one of the big downsides is that the surrounding business code has sometimes a significant effect on the performance of Mnesia. So transaction ID in Mnesia is composed of a PID of the calling process and a Lampert clock, which is maintained internally by Mnesia. Originally, all side effects of the transactions are stored in an unnamed ETS back table, and they remain there until the transaction commits. I will again briefly, I will again skip a lot of things. I will just mention that logs held by the transactions are global, and each read and write inside the transaction grabs a log, and this operation is replicated across the entire cluster. Two-phase commit, very standard. Now we're to the last part. Suppose the transaction commit has succeeded. In the last stage, it is performed on all nodes. The transaction dumps contents of the shadow back table to the real table, so other transactions can access it. Here Mnesia sends events and updates SNMP. Okay, so let me slow down a little, because we passed the part which you probably all know. So when we analyze performance of Mnesia transaction, First, we notice that during the commit phase, Mnesia does selective receives in order to collect votes and outcomes. So Erlang has to scan the mailbox of all processes. Unfortunately, Mnesia doesn't use a ref trick, so if the message queue of the process calling Mnesia transaction is 1, we're out of luck. Thankfully, it's a trivial problem to solve. Just create a temporary worker process. The second problem is that during commit, Mnesia has to broadcast pretty much all operations to the entire cluster and then wait for the outcome. And the number of such messages grows linearly with the cluster size. And solving this problem is pretty much what we did in Mria. So this leads us to a Mria project. We wanted MQX cluster to be horizontally scalable, and Mnesia was an obstacle on this path, so it had to be fixed. On the other hand, we wanted to reuse as much of trusted Mnesia code as possible and focus our efforts only on the newly added parts. We also wanted to avoid divergence from the OTP upstream, so to be able to update to the new Erlang versions. We needed extremely low latency dirty reads because they're performed for each message that we route, but latency of writes could be sacrificed in favor of write throughput. Because we already use dirty reads in the hot paths, it was okay to lose some of serializability guarantees, but it would be nice to have them as a backup if required by business applications for some reason. This led us to a mixed architecture that combined the existing Mnesia commit protocol with a custom, eventually consistent protocol. We split large Mnesia cluster into several smaller ones and then synchronized data between them using a custom protocol. We further simplified the design by assigning each node one of the two roles, core or replicant. Core nodes are very similar to the regular Mnesia nodes, and replicant nodes are read-only. This helped us to simplify the replication protocol even further by making sure that the transaction logs flow strictly in one direction. When a replicant needs to update the table when behind the scenes, Mria sends RPC to one of the core nodes, which executes transactions on its behalf. From Mnesia perspective, replicant nodes don't exist, so it does not have to broadcast any decisions to them. Also, we can freely add and remove them. Database is a very complex and mission-critical application, so we took testing and verification very seriously. We used Concurror for unit testing as much as possible, so we could reliably explore all possible scheduling of the processes in our finite unit tests and find all possible race conditions and deadlocks. Unfortunately, we could not cover the entire code base by Concurror because it cannot emulate input-output. So Mnesia does a lot of input-output, and we had to resort to different approach using trace-based Snapcafe test suites. Snapcafe is a library which allows to capture trace events from processes as long as they're manually instrumented with trace points, and then analyze history of program execution offline. It also allows to inject random faults or delays into the system, so we could emulate failures or explore rare execution paths and stress test our supervision trees. It does not perform exhaustive analysis like Concurror, but it can deal with I/O. So we used a combination of two approaches. Finally, as an experiment, we did small-scale formal verification using Coq Proof Assistant. So Mria consists of several processes. On the core node, we have RLog server. RLog stands for replication log, which collects transactions captured from Mnesia. A set of RLog agents are created dynamically for each replicant, and they help to buffer transactions and isolate faults should one of the replicant fail. And we also have a set of temporary bootstrap server processes. On the replicant side, we have a load balancer that allows replicants to distribute the load between the core nodes more or less evenly. RLog replica processes that orchestrate the whole transaction import flow. RLog importer worker that dumps the transaction logs to the local replicas, and a temporary bootstrap client. Now let's dive into design. First, we added a small patch to OTP, which allowed us to intercept transactions in the post-commit phase. This way, we got a real-time stream of committed transactions. The whole transaction replication process is initialized by the replicant when it connects to the core nodes and requests an agent to be created. The interesting part is how we backfill the old data. We call this process bootstrapping, and we use algorithm that does not require any lock-in whatsoever, so it does not disturb any transactions. It is facilitated by two processes, Bootstrap server on the core and Bootstrap client on the replicant. Bootstrap server goes through all existing records in the database and sends them over to the client, which dumps them to the local replica. Of course, at the same time, other transactions can modify the tables, so obviously this produces a totally corrupted, unusable replica of the tables at first. So let's consider an example. So tlog is a list of operations that are applied in real time, and bottom two rows represent state of the core node table and replicant table as bootstrap process progresses. So imagine we had a write operation in the translog. Bootstrapper picks this operation up. Same here. This operation is picked up. But now what happens if some transaction updates a key which has been already sent to the replicant? Of course, the side effect is lost. Same happens if the bootstrap process reads some key and when a delete happens. Once again, we lose this operation, so we end up in inconsistent state. But turns out we can salvage the data if a replicant subscribes to the real-time transaction log before starting the bootstrap process and buffers the transactions while it's running. So after the backfilling is complete with some operations missing, as we saw earlier, the replicant can replay the buffered transactions, and it will make the replica consistent. Had a nice formal proof of this, but unfortunately I have to skip it. So this leads us to the design of the replicant state machine. So it starts in disconnected state. When it establishes a connection, it starts collecting the transaction logs from the upstream while Bootstrap is running. When it enters local replay state, where it replaces the buffered transactions. And finally, it enters normal operation, where the transaction logs are applied in real time, although with some delay, because our protocol is asynchronous. This is a really interesting part, but unfortunately I have to glance over it and go straight to the benchmarking. Let's talk about performance. We mostly used Linux kernel network emulator, or NetEm, to explore how Mria clusters handle network latency in comparison with Mnesia. We used load generator that continuously created small Mnesia transactions, reading set of 10 different keys, and then updating the values for these keys. We allowed this generator to run for a period of time and then measured average transaction time. This experiment was repeated for different values of network latency and different cluster sizes. When Mria was used as a database backend, we used at most 2 core nodes and n minus 2 replicants. In case of Mnesia, all the nodes were the same. Let's look at the results. First, we consider a simple case where we have only one load generator process. On this diagram, we can see that transaction time for Mria plateaus after we add 2 nodes, because the rest of the nodes are replicants and everything happens asynchronously for the replicants. While for Mnesia, the transaction time continues to grow with each added node, ever so slightly. We also see that until the graphs diverge, transaction time for Mria and Mnesia are about the same. So Mria does not introduce a lot of overhead, which is good news. On the other hand, so far the improvement does not look too impressive. This is because in this benchmark, Mnesia is in its absolute best position. With a single load generator, it can generate all the broadcast requests in parallel, and all the receives are coherent. So the round trips don't add up. Things start to change when we create multiple load generators, and commit messages are no longer coherent. Here we start to see that Mria really starts to take the lead. However, we also notice an increasing trend in the Mria transaction time as well, which is a little bit disappointing because ideally we would like to see transaction time to plateau like on the previous graph. Unfortunately, it has nothing to do with Mria replication protocol, but rather its limitation of how Mnesia itself handles parallel transactions. This can be demonstrated by moving all load generator processes to a single node. So the network latency is out of the picture, but we still see the similar situation here. So conclusion, overall, Mria project turned out to be a success. In addition to the synthetic tests, we also run large-scale benchmarks of MQX broker with all its business applications, and we also demonstrated improvements in their performance and scalability. As a side effect of this project, we ended up with a rather extensive test suite and the benchmark for Mnesia-like databases, utilizing a variety of tools and techniques. So the next logical step for us and for the Mria project is to replace the remaining parts of Mnesia with the custom code and hopefully achieve an even faster transaction replication. And that's about it. Thank you for your attention and sorry for the technical problems.
Hello. There we go. Hello.
Wow.
Yeah. Thank you so much, Dmitrii. Do we have any questions? I do have one question. So can you repeat again, how did you use formal methods? In this case, I think Cork in the development. Yeah.
Okay, so let me briefly go to this slide. Okay, which slide was? Okay, so basically, we did not attempt to try and formally verify a parallel system or distributed system, although I know that such works exist. But it's, I would say it's pretty much cutting-edge research. So instead, we went for low-hanging fruit, and we simply verified whatever algorithms of important transaction logs which involve duplicating, reordering, or deleting records in the transaction logs. So such properties can be verified pretty easily. So, for example, when we were talking about the dirty bootstrap procedure, we noticed that while we ran the bootstrap, we end up with a state where we went through all the records that existed and some snapshot of the past. And then we applied a set of operations with random operations dropped. Then we replayed the transaction log on top of this corrupted state. So we modeled this whole situation in Coq using an abstract definition of a key value storage with some pretty trivial operations like create new storage, update value, delete, read, etc. This storage was defined, like the semantic of the storage was defined through a set of trivial axioms, like if you write a value to a key value storage and then you immediately read it, then you get the same value that you've written. That if you update one key, it does not affect other keys, etc. Turns out this fairly general definition is fairly useful. So if we define properties like two key value storage are equivalent if we can read all keys and we always get the same result for each key, and we consider this key value storage equivalent. And this way we were able to reason about some algorithms where we could where we dropped some transaction logs or reordered them. For example, we formally defined this lossy transaction log what we discussed in the bootstrap stage, and then we were able to do a fairly boring inductive proof that this property is indeed true. Yeah.
Great. Thank you so much.